Okay, I just wanted to give you one last little bit on the second part of the energy lab we did in class. So if you're in Mr. Eaton's room, y'all did it differently, so you should not, I mean, you can listen to this video, but it's not what you did on the lab. What my classes did was we put a car up here. We measured its height with a meter stick, right? So that's H. And we put a motion sensor down here, right? Hooked to the LabQuest. And so what we know is UG should equal EK as long as the work done by friction is negligible. So that means F friction dot X, right? Work is F dot X. So if friction isn't, when I say work done by friction, I mean if the car, you know, was traveling this way and it had a certain amount of UG right there, if friction were going to do work on it, then there would be a frictional force here, right, acting. So there would be F friction acting through some displacement X this way, yeah, and that would mean that if I started out with 100 joules of gravitational potential, then it would equal the kinetic energy at the bottom, right, plus whatever work was done by friction, right? So maybe friction turned 20 joules into thermal, so that would mean I would only be able to have 80 joules of energy of motion. Okay, but we said that's not the case. We said friction is negligible, so I'm going to clear this. I'm going to say again, we had a car here. We measured the height, right? So we know UG should equal EK at the bottom. When it's all the way at the bottom, we had a motion sensor and a LabQuest 2 or whatever. Our height is measured from here to here. So like I told you before, I'd like to see you say first, conservation of energy. If it were Newton's second law, if it were something else, you would write that first, right? Then say UG equals EK. Then say, so this is kind of the order of operations. Then say MGH equals 1/2 mv squared, right? The mass is not a factor here if I can cancel it out, right? So if, I believe in this particular lab, my students, we wanted to find the relationship, and I talked about this in the previous video, between EK in joules and V in meters per second. If we just look at the way the equation is written, 1/2 mv squared, we know this should come out like this. Then we would have to linearize it by doing V squared in meters squared per second squared. Yeah. So this would also be EK in joules. We could linearize it like that. Okay, but the trick is in knowing that the UG here is going to equal the EK here, right? So you're measuring UG, right? You're measuring height. You know G. You don't need M. So, but you can measure, you know, everything here, and then you set it equal to what's at the bottom, and you can measure V, right? So I can say that if I know, and I think, guys, in ours, so I think in our lab, you might even have masked the car. But in truth, it wouldn't matter because it's just like multiplying each side by the same number. So, but it would be fine if you said you masked the car. But I mean, if you know this number right here, let's say you did mask the car. So let's say the UG is 100 joules. All right. Then you know and you know the velocity, right, v squared, then you should be able to plot EK, right, versus V, see that it's quadratic, EK versus V squared, see that it's linear, and then whatever the slope is of this one should equal, in this case, half the mass. But that was kind of your job there. Okay, thank you for coming. I had a nice time.